Channel Incredible Maths. In this video, we will solve a problem asked in Csir June 2023. This problem is related to calculus of variation and this is under part C. So given that the function I of x equal to integral 0 to 1 y square minus 4 y dash plus 4 y dash square dx subject to the condition y of 0 equal to 1 and y dash of 0 equal to 1 by 2. So we need to find which of the following statements are true. So this is a part C question, so we have to solve carefully. So first we will find the function y of x. So here we will use Euler-Lagrange condition to solve this problem. So the Euler-Lagrange equation is fy minus d by dx of fy dash equal to 0. So where this is our f. So our f is y square minus 4y y dash plus 4y dash square. So we will find fy. So fy is 2y, partial differentiation with respect to y, minus 4y dash, so this becomes 0. And fy dash is 0 minus 4y, y dash will become 1, and 4y dash square will become 8y dash. So let it be equation 1. So now equation 1 implies, so fy is 2y minus 4y dash minus d by dx of fy dash is minus 4y plus y dash equal to 0. Now 2y minus 4y dash, so differentiating this with respect to s, so we get minus or minus plus. So first 4y dash and here it will become minus 8y double dash equal to 0. So this and this will get cancelled. So finally we have 8y double dash minus 2y equal to 0. So solving this, you will get y double dash minus 1 by 4 y equal to 0. So this is a second order ordinary differential equation. So which is a second order ordinary differential equation. Moreover, it is homogeneous and also linear. So a linear homogeneous equation with constant coefficients. So therefore we have to solve this using the concept of auxiliary equation. So the auxiliary equation corresponding to the differential equation is m square minus 1 by 4 equal to 0. So solving for m, we will get m is equal to plus or minus 1 by 2. So here the roots are real and distinct. So the roots are real and distinct. So therefore the solution is y of x equal to c1 e power 1 by 2x plus c2 e power minus 1 by 2x. So here we need to find the arbitrary constant c1 and c2. So using the condition defined on y. So the condition defined here is y of 0 equal to 1 and y dash of 0 equal to 1 by 2. So we will write the condition. So the condition is y of 0 equal to 1 and y dash of 0 equal to 1 by 2. So we will find y dash of x. So y dash of x equal to differentiating e power 1 by 2x gives us half times e power 1 by 2x. So we have c1 by 2 e power 1 by 2x, and here we will be having minus 1 by 2. So minus c2 by 2 e power minus 1 by 2x. Now using the first condition y of 0 equal to 1, so this implies 1 equal to c1 plus c2. Now y dash of 0 equal to 1 by 2, so this gives us 1 by 2 equal to c1. So e power 0 is 1 and here e power 0 is 1. So c1 by 2 minus c2 by 2. So we can cancel this 2 Okay, so this implies C1 plus C2 equal to 1. So multiplying by 2, so we get C1 minus C2 equal to 1. So now we can solve these simultaneous equations. So this becomes 2C1 equal to 2. So therefore our C1 is 1. So from this we can get C2. So what is C2? C2 is 0. So when we substitute C1 equal to 1 here, so C2 equal to 1 minus 1, so it's 0. So therefore our y is C1 is 1 and C2 is 0, so therefore y equal to e power of 1 by 2x. So this is our function. So based on this function, so we have to choose the option. So here this function, so first two option deals with the convexity of the function. So we have to find whether it is a convex or concave. So if it is convex, if it is then it will not be concave. So here so when we draw the function, so we draw the graph of this function. So e power x is like this. So this is e power 1 by 2x, and this will be some 0, 1. When x is equal to 0, y will be equal to 1. So this is our y equal to this one. So we have the condition to check the given function is convex or not. So suppose if a function is differentiable, so here function is differential function, so we will see what is the condition for a differentiable function to be convex. So a differentiable function y of x is convex function on an interval if and only if its derivative y dash of x is monotonically non-decreasing on that interval. So this one condition, some remark, and another one is, suppose a function is not differentiable, then if graph of y of x lies above all of its tangents, then y of x is a convex function. So here the function y equal to e power 1 by 2x is a convex function because it's a differential function. So we can say it's a differential function and its derivative. So derivative is, so what is the derivative? So derivative is 1 by 2 e power 1 by 2x. So it is a non-decreasing, that is it is an increasing function, therefore it is a convex. So it's a convex function. And also, so we can check using this also. So graph of this function y of x lies above all of its tangents. So it's a tangent so the graph lies above all of its tangent. So therefore it's a convex function. So therefore the first option is correct and The second option is wrong. And so we can easily see that the option C is also correct. So exponential function satisfies this property. So anyway, we will check y of x plus 1. So C is y of x1 plus x2 equal to y of x1 into y of x2. So now y of x1 plus x2 is e power 1 by 2. Our function is y. x1 plus x2, so this can be written as e power x1 by 2 plus x2 by 2, so this can be written as e power x1 by 2 into e power x2 by 2. So this is our y1 and this is our y2. So therefore option C is correct. And let's see the option D. So option D will be wrong. So that is, so option D is y of x1 x2 equal to y of x1 plus y of x2. So now let us calculate y of x1 x2. So this is equal to e power 1 by 2 x1 x2, and y of x1 is e power 1 by 2 x1, and y of x2 is e power 1 by 2 x2. Y of x1 into y of x2 is e power 1 by 2 x1 into e power 1 by 2 x2. So this is equal to e power, so 1 by 2 times x1 plus x2. So that is y of x1 x2 is not equal to y of x1 into y of x2. So therefore option D is wrong. So the only two correct options for this question is option A and option C. So if you like the content of this video, kindly like and share with your friends. Also subscribe our channel. Thank you.